So sequences are very common structures in programming. In fact, even if you go to the oldest programming languages that we have, like Fortran and Lisp, they both provide sequences. Fortran did it in the form of the array, and Lisp did it in a more abstract way, very similar to a linked list. So to manipulate this in programming languages, we need a different definition of a sequence. Before I told you is an order collection. So now I do something which is completely different, but you can show they are similar. And so I'm telling you this. A sequence is either of two things. One is a special value that I call nil. Other words are empty, null, zip, zero. This is one case. The other case is that a sequence is a pair. Two things. The first one is an element, and the second is a sequence. And of course, you can say, I don't really like this one. Because to tell me what is a sequence, you tell me that something else is a sequence. How can I understand it if I haven't understood yet what is a sequence? So this is a recursive definition, and takes a while to sink in. Have you ever seen this definition? Yes. When you do linked list in your favorite language, what is a linked list? It's either zero, you call it a null pointer, but a null pointer is zero, right? In fact, you can even write it as zero. Easy. Or is a struct, and what do you put in this struct? You put an element and a pointer, which is a sequence. So you have used this all along. The pair in this context is called a cons, sometimes you call it a cell, because the language Lisp, which introduced this concept, used to call a nil the empty sequence, and cons the sequence where you have an element and another sequence. Alright? Now we're going to play a little bit with this, also to do more recursion. By the way, talking about recursion, did you like the coin change? Did anyone try to avoid the duplicates by keeping those things ordered? No one. How disappointing. Tuples? I wouldn't see how. Maybe you see it and you show it to me. Alright, so by way of notation, if A is an alphabet, we also use the same symbol for a language. And of course, this is a disgrace. But people do it, so we have to go with conventions, right? And so if A is an alphabet, then what is the language A? This is the language where every string consists of one character of the alphabet. So here we confuse strings of one character and the character themselves. In your favorite language, you write one this way and the other one this way. You see the difference? So here, because we don't put the quotes, we cannot distinguish one from the other. Right? Because we don't write the quotes. And so now we have a language and we have an alphabet. They are two very different things, and we write the element inside the same. Does it offend you? Not really. We don't write the quote, so this is perfectly fine. All right. So, if we have to manipulate a sequence defined inductively in that way, when I give you a sequence, what are the things you can do? First, you check whether it is a nil or a const, right? If it is a constant, what are the things that you can do? You can only work on the head or the first slot of the pair or the second slot. So we call head and tail. These are the only thing you can do, right? You remember when we talked about the monkey getting the banana where you have the box and the stick to do the job? So here is the same. The boxes and sticks that you have are work on the head and work on the tail because it's the only thing you know. So now I want to define a function that computes the length of a sequence or a string. Let me make this a little bit bigger. So I call this my len because of course any decent language that manipulated these things already has a len function defined there. So I don't want to use that one. And so I want to compute the length of a sequence. What is the length? The number of elements, right? The number of times you find a pair that has a first element and a tail. So, how do I do this? What do I know about the sequence? Yes?
Would you just linearly traverse it and count as you go?
Well, here I have to say x. Let me call this x. X is my sequence, right? So, what do I do here? So I told you that the sequence is either nil or const, right? So we have to make this distinction. In this language, nil is written in this way, and const, which is a pair, is written in this way. When the pair is a list where the first is an element and the second is a sequence, instead of putting the comma here, I put the colon. So when you read it, you know what I'm talking about, for your convenience. And so, what is the length of the first? So, the length is a number, right? So, my length of that one, how many elements there are there? Zero. Oops. What is the length of the second? Say it again. Fantastic. You made my day. 1 plus my len of xs. Yeah? Could it be more natural? All right, so because I'm not using x here, right, which is the first. In fact, it doesn't really matter what is when I compute the length. So I take out his name, otherwise the compiler will tell me, look, maybe you are making an error here because you have a variable called x, but you never use it. So in that way, I say, look, this is a variable that I'm not going to look at. So now let me make a list here. Let me call it my list. So if this is a list of 3 elements, how do I write it? Suppose that the first element is 4. Then what do I have? The second element is 7, and the third element is 2. Now I have the empty list, and I close everything. This is the list made by 472. You with me? According to the definition. And so now I say main equal my len of my list. You with me? I load it. Oh, sorry, I put an extra quote at the end. All right. So now I call main. What do you expect? Three. So here I use the recursive inductive definition of list. List is either a nil or a const. And then I compute the length by saying, first let me see whether it is a nil or a const. If it is a nil, the length is 0. If it is a const, it's one more the length of what is following, right? Yes?
So the null is just basically your base case.
Yes.
That's just a recursive function.
Yes, this is a recursive function where one is the base case and the other one is the recursive one. So far so good? Should I do another one? Yes?
So this, in this example, it's you're using a very explicit sequence of 4 to 7 to 3.
Yes.
Does the inductive definition of sequences also work for generalized sequences like 2 to the x or something like that?
Yes. Now, there is an easier way to write this one, right? I mean, this is really ugly, right? And the more you have, the more parentheses you have to close. It's a disgrace. So, the language is nice. So the language allows you, this is comment, allows you to write it in this way, which is much nicer, right? And so now if I reload it and I call main again, works the same way. But it's interesting because this one really defines the list according to the inductive definition. And here defines the list according to the non-inductive, which this is an ordered collection of elements. If you look at this one, this is much easier to understand, right? Because when you call my length on this one, what do you do? This 4 matches this anonymous variable, is disregarded. XS is this part here, the 7 and the 2. So this is 1 plus my length of this one. And you keep it going down until you get the base case. Yeah? All right. So suppose that I want to check whether in a list there is the number 5. Write it in 1 minute, the definition. Here, I want to check whether in a list there is the number 5. In this list I will say false. In another list where there is 5, I will say true. Try to write it. Maybe you don't write it 100%, but you should write it at least 75. Then we see why that 25 is missing, and we fix it. All right. Did you make it? So contains 5 of the empty list is false. Contains 5 of a list that start with X and this is the rest of the list, what is it? If X is 5, the answer is true. Otherwise, 5 must be contained in the table, right? You see? You keep going until either you hit the 5 and you return true. It doesn't matter whether you evaluated this or not, right? Or you hit the bottom and say, I haven't found any 5, so there is no 5. Should I run it? So, main 2, false. Main 3, true. So what is the general principle here when you have to write a recursive function on a sequence? The base case, supposedly you know the result. Otherwise, in that case, what you do? You apply the function to the tails, and then you massage the result with the head. And the kind of massage depends on what you are doing. If you want the length, then you add 1. If you want to see whether this one contains 5, you have to do an OR. By the way, you recognize that this is an OR, right? Like in your favorite language. Should we concatenate the two lists? We saw this already, but what is the concatenation of two lists? Concatenation of two lists is that if you have a list here where you have a 4, 7, 2 and another list where you have a 1, 5 and 3, the result will be a longer list where you have a 4, 7, 2, 1, 5, 3. Yeah? So how do we do this one? Again, we pick the right list because now we have 2. We check whether it is nil or cons. Depending on whether it is nil or cons, we do one thing or we do the other. Yeah? They're all the same, cookie cutter. The only thing that differs is how you massage the recursive case. And so here, if this one is the empty list, when you do the concatenation, what do you find? The second. So, here, I call this my append. Empty list and a list ys is equal ys. Yes, thank you. My append of x and a tail with ys is equal to what? So let's go back here and I tell you what I want to do. Here I'm in this situation where this is ys. This part here is xs and this is x. Yeah? So I say, let me take x out. So I have now, here I have my x, which is 4. Here I have 7 and 2. And here I have ys, which is 1, 5, and 3. Right? What do I do here? Fantastic. You concatenate these two and you get what? 7, 2, 1, 5, and 3. Right? I combined these two. Now, what do you do with this one? Stick it to the front. How do you stick it to the front? Cons. Cons. So, this one will be x cons with what? My append xs ys. Yeah? And so main 4 will be my append of what do I had? 472 153. Let me reload it. Main 4, here it is. As you see, in all cases, I have the function. I check whether it is empty or is a pair. If it is empty, I find a result somehow. If it is not, I call it the function that I'm computing on the table. Of course, there are cases which are more complicated. This is the general idea and works 80 or 90% of the cases. Yeah? Did we move on? Now, if you take other classes and you have to solve the problems, either with numbers or with sequences, do it in whatever way your instructor is asking you. In the back of your mind, think about doing this way. This is a great practice. Yes?
What program do you want to use this?
So, this is called Curry, and you find information on my website. And there is another language which is called Haskell, which is very similar to this, that allows you, the syntax is even the same. There is a language which is a simplification of a list, which is called Scheme, that some 10 years ago a lot of schools introduced it to teach programming instead of C or Java, with mixed results. All right, so I hope programming was fun for a second. So now we talk about induction. So what is the problem here? The problem is that we want to prove some statement for every natural number. 0, 1, 2, 3, 4, and so on. What is the potential problem? The natural numbers are infinite. So you cannot prove it for 0 and then for 1 and then for 2. You want to prove it for all, you spend the rest of your life and you'll never get it. Right? So we need something to do this. And so this is called principle of induction. And this was invented by a guy that was the first one to say what the natural numbers are. And interestingly enough, and not surprisingly, the definition was inductive. He said that 0 is a natural number. If x is a natural number, the successor of x is a natural number. And when he had to prove things, he had to invent the principle of induction, because otherwise there is no other way to do it. Principle, because this is something that we don't discuss, we accept. This is not a theorem that we prove, but it's an agreement. We agree that if we prove it in that way, it's true. And so, what are the steps? First, you have a statement parameterized by a natural number. What does it mean, parameterized? Your statement is like a function in C or a method in C++ that one argument is n. And then inside you do something for n. And in your language you can call it for n equal 1 or 2 or 25 or whatever you want. So you have a statement parameterized by that. Let's see an example. My statement is this one equal to this one, where n is the parameter. Is also the only parameter because I is not a parameter. I varies from here, so it doesn't appear. Alright? This is my statement. And so now I want to prove that this one is true no matter what n is. N is a natural number. So how do I do it? First, you prove it for n equals 0. What does it mean? With an editor, in fact, this is exactly what I did here. With an editor, I change all this n in 0, and then I verified that this is true. Yeah? Then you do the following. You assume that this statement is true when this n is some k. We don't know which k. K is greater than or equal to 0. It's some generic k. And so we assume it, and again, with the editor, I change all the n in k. I assume that this one is true, and I prove that it's true when n is replaced by k plus 1. Again, with the editor, I replace every n with a k plus 1. And this is what I have to prove. Now, some people are a little bit concerned by this assumption. Because this assumption says, look, you just change n into k, it doesn't change anything. It's like you have a method or a function where you change the name of the argument from n to k everywhere. It's exactly the same thing as before. Right? And we assume that this is true. Is this really true? We don't care. This is a principle. If we agree on the principle says to do this one. So, we assume that this is true, and we prove that the other one is true. Again, you remember the difference between the crazy and the neurotic one, right? So don't be neurotic about this one. This is a principle. We can argue, and eventually I will, why this makes a lot of sense. And so, you have the statement. You do the replacement with 0 and you prove it. You prove that if it is true with the replacement with k is true for k plus 1. And finally, you conclude that then this statement is true for every n. Alright? Should I do it?
So, in the part that we assume,
Yes?
why do we do k right there on equal 0? Because we already did the 0 case.
Yes.
So, shouldn't it be just greater than 0?
We'll get to that. If I forgot, remind me again. All right, so my statement. P of n is summation I 0 to n of I equal n times n plus 1 divided by 2. All right? This is P of n. So the very first thing is prove P of 0. So P of 0 is this one where I replace n with 0. So I have I from 0 to 0. I equals 0 times 0 plus 1 divided by 2. I haven't done anything. I just copy the one where I replace n with 0. Is that equality true or not? On this side, I add from 0 to 0, 0. There is only 0. On the other side, I multiply 0 times and divide is 0. So, this has been verified. You with me? So now, assume and I take again this one with a k. I equals 0 to k of I is equal k plus 1 divided by 2. I assume. But is it true or not? We don't care. Alright? And so, with this assumption, prove what? I do this one with k plus 1. This one is k plus 2, but I write it in this way, so you really see that I start from the top and I replace n with k plus 1. Alright, I have to put a parenthesis because otherwise change the meaning. Yeah? Alright, so let me write this one here. This is a question mark. I have to prove this one. Alright? So this one is not a question mark. What is this one here? This is the summation I from 0 to k of I plus k plus 1. You with me? When I add from I to k plus 1, I can add from I to k and then add k plus 1. Okay? So now, what is this here? This here is the same as this here, right? Because I assume that they are the same, here I can put a k plus 1 divided by 2. And then I have the other piece, which is k plus 1. Yeah? So this one is also k plus 1 times 2 divided 2. Yeah? And so this one becomes what? K plus, under I have a 2. I'm sorry? Yes? Times k plus sorry, I got lost.
K squared plus 1. Oh, K squared plus K.
This is a 2, so this will be 2k plus 2 okay, so let me restart. So this one is I follow here, this one is this one, which is k plus 1 divided by 2 plus k plus 1. Yeah? So now I factorize this k plus 1. So here I have a k plus 1 times k divided by 2 plus k plus 1. Yeah?
K squared plus K.
Sorry, this is a 1. All right. Yeah? You with me? So this one is what? This is k divided by 2 plus 2 divided by 2, right? And so this one is k plus 2 divided by 2. And so the final result is k plus 1 times k plus 2 divided by 2, which is exactly what I had to prove here. And so I verified this Question mark. Yeah? And so this is written very nicely in the notes now. And you see the proof here. Yes? Is everyone on board? So this is an interesting formula which was invented by Gauss when he was a kid. And I tell you the story because it's funny. He had a teacher, and like all teachers, he was lazy and nasty. And he would give the kids to do this. Add all the number between 25 and 50. So 25 plus 26 plus 27 plus 50. Oh, yes. And so in the morning in the class I would say, do this one, and then he would mind his own business and the kid would do. This was a time where they didn't have a pen and paper. They had a blackboard, and they would write with chalk on the blackboard and then click to go back. And so he gave this to Gauss, and Gauss takes this for 30 seconds or a minute and goes there with the solution. And so this was the very good old time where the teachers had this one and they would use it on the students. Unfortunately, I cannot do it, but I'm sure you would learn much better if I do it. And so he said, I'll take care of you later. And so all the kids spend the morning doing this and turn it in. And finally, the teacher looked at the board of Gauss and was right. How did he do it in seconds? How did he do it in seconds? And so this is the way. If you add these two, what do you get? 75, right? Yes? If you add these two, what do you get? Another 75, right? And if you add these two, what do you get? Another 75. How many do you get of this one? How many numbers there are between 25 and 50? Well, there is the first one and the last one, right? So they are 26. You with me? 26. So how many 75 you have? 13. So what is 75 times 13? And so this is the result. Oh, sorry. I did the multiplication, and this is the result. Good enough? Smart kid. Of course, he is considered the greatest mathematician that ever lived. And when he was grown up, he discovered beautiful things. And once in a while, someone would send him 10% of what he did. And he would say, oh, this is great, this is great. Work more on this. There are more interesting things to discover. All right. All right, a variation of induction. Oh, you are not seeing it. So there are a couple of variations of induction, and we are going to look at this. One is that the base starts with a number greater than 0. So suppose that you consider a polygon. Let me write here a polygon. A polygon like this one. All right, you see the polygon? So how many diagonals there are in a polygon? In this one there is 1, 2, 3, 4, and 5. You see? So suppose that you want to prove by induction that if the polygons are an n side, there are some formula of n diagonals, like n times n plus 5 divided by 4, or something like that. I don't know what it is. So if you want to prove this by induction on the number of sides, you need at least 3 sides to have a polygon. If you have less than 3 sides, you don't have a polygon, right? And so here the induction must start at 3. You cannot start it at 0, because at 0 you don't have any polygon, there are no diagonals. You with me? And so, when you prove this one, for some cases, the formula doesn't work for 1 or 0 or 2. You have to start with a greater number. And so, you start with a base, and then you prove for k greater than or equal that one, and this also for all the numbers starting with that base. Alright? We can try to do this one, or you can play a little bit with the idea. And this is one possibility. This is one variation of induction. The other variation with induction is that if you look here, I say, prove it for k, assume it for k, and prove it for k plus 1. So here, there is a variation that says, assume it for 0, 1, 2, 3, 4, up to k, and prove it for k plus 1. Instead of from k to go to k plus 1, you go for all the values up to k, and you go to k plus 1. All right? So here you have an example. If you have stamps, 4 cents and 5 cents, you can make any postage you want starting at 12. So this one uses both. So for example, if you want to make any postage where you have at least a 12, and now with 12 you don't send anything. I think the smaller you send the postcard probably is 30 or so. If you have stamps 4 and 5, you can do anything you want. You don't need anything else. Starting at 12. Should we prove this by induction? All right. So here, I prove it for 12. This is the base case. How do I make a 12 with a 4 and 5 postage? 4 times 4. Now, I also prove it for 13, 14, and 15. Yes, thank you. 3 times 4. This one is what? 2 times 4 and a 5. Yeah? This one is 1 times 4 plus 2, 5. Yeah? And this one is 3 times 5. Yes? So now let's pick a number like 87. You want to make a posted 87. So we assume that you can make it for all the number below. So we assume that is true for 86, 85, up to 12, because we started at 12, right? We know how to do it for those. And so, if you assume that you can do it for all these, how do you do it for 87? It's been a long lecture. So, if you can do it for all this one, you can do it for 83, right? And you add 4 and you get 87. So, if you assume that you can do it for 83, then you can do it for 87. This is why it's convenient to assume for all the one that comes before. Yeah? Too easy?
So the next thing was 86 plus 1.
Yeah, but you don't have one. You only have 4 and 5. Or you can assume that you can, instead of 83, you can do it for 82, and you add a 5. And probably you can do it both ways. Alright, if you're close here, wish you a great weekend. It'll be sunny, 50 degrees on Sunday. Enjoy.